Hello everyone, my name is Anvu Võ. I and my colleagues at UCD are working on spatial data analysis approaches for detection of subterranean structures in cities. This work is part of UrbanArc, a US-Ireland research and development project on harnessing remote sensing data for urban flood risk assessment and communication. To date, we have successfully developed a simple but efficient algorithm that extracts subterranean points from large 3D point clouds. I'm presenting here an example of the output we obtained from the algorithm. You are seeing a 3D point cloud colored in gray, and the green points overlaying the point cloud are the subterranean points that were automatically extracted. Here you can see an outdoor staircase that leads from the ground level to a basement at the back of a tall buildings in the Dublin city centre. You may recognize the building we are seeing. This is the Science Gallery on Trinity College Dublin's campus. Across the road from the Science Gallery, we have some junction terrace houses. The houses have some basements in front of them, and the back gardens are lower than the surrounding terrain. All of those were successfully picked up by the algorithm I'm presenting today. The reason we in UrbanArc are interested in developing such an algorithm is because subterranean structures have an important role in flood risk assessment. First, the structures laying below the ground level, particularly those used for residential purposes, are exposed to a higher risk of flooding, and we need the knowledge of such structures to better analyze the risk. Second, we see that subterranean structures are important for accurately predicting flooding. Those structures have impacts on the dynamics of the flood flow as well as the inundation level in a flood event. But most existing flood models do not account for the impacts of subterranean structures. And we are not the only ones who see the importance of subterranean structures in flood risk assessment. You are seeing here on the screen some excerpts from the regional drainage policies for the Greater Dublin area. They are too long, please don't read them. What the document says here is that there is a need for the local authorities to establish and maintain a database of basements for the purpose of assessing the extent of basement flooding. The database should have information about the location, the floor level, and the use of the basements, as well as information on historic floodings. However, the same document says that while the need is here, there is not such a database available. The Dublin City Council has two databases, but neither of them is complete, nor they have the right information for the purposes. Now coming back to our algorithms, I wanted to start with the three adjectives that describe the characteristics of the algorithm. The first adjective is simple. The algorithm is based on a very simple principle. The second one is scalable. As a distributed algorithm, the algorithm is designed to work with a large amount of data and to cope with future increases in the data volume to be analyzed. And the third one is robust. We have tested the algorithm under a few different scenarios using different kinds of data, and we see that the algorithm worked consistently. So here's the simple principle behind the algorithm. The data to be analyzed is a 3D point cloud that contains geometric samples from the terrain as well as above ground and below ground objects. We assume that we have a digital terrain model that gives us the ground elevation over the area of interest. So those are shown in red color. When we integrate the point cloud and the corresponding DTM, we can separate the subterranean points from the rest of the point cloud, and that is how we go about our task. You see that the core computation here is to train the input point cloud and the digital terrain model, or the DTM, so that we can line up each point in the point cloud with its corresponding ground elevation. The point cloud is irregularly distributed as you see in the figure on the left hand side, And unlike the point cloud, the DTM is often represented as a raster, meaning that the elevation values are structured in a regular spatial grid consisting of cells or pixels arranged in columns and rows, as you see in the figure on the right-hand side. Looking deeper, you see that each point in the point cloud is represented as a triplet of x, y, z coordinates, usually in a geographic coordinate system. And each raster cell in the DTM is represented by its raster index and an elevation value z. The raster index is a two tuple that contains the row index and the column index of the cell, which are defined in the discrete coordinate system of the raster. So our job is to join the two datasets. To do that, we need a common key that links the two sets. We see that we can use the raster index for the purpose, and know that the point cloud doesn't have a raster key, so we need to compute that. The computation is called rasterization, which is essentially a transformation of the point cloud from its original geographic coordinate system to the discrete coordinate system of the DTM raster. That transformation can be expressed using the equation shown on the screen. In the equation, x and y are the original geographic coordinates. x0 and y0 are the geographic coordinates of an arbitrary corner of a raster cell, and c is the raster cell size. After we have the raster keys for both of the datasets, the join is straightforward. However, one thing I did not mention is that we are dealing with large volumes of data. Each of the datasets we are joining here can contain multiple billions of records, and we expect the amount of data to be analyzed will increase rapidly in the near future when there are more and more large-scale, high-resolution datasets being collected, and the data acquisition technologies keep advancing. To overcome the data volume challenge, we decided to opt for distributed computing, which allows us to use multiple computing nodes in a computing cluster to perform the computation in parallel. More specifically, we use Apache Spark, which is a successor of the MapReduce framework for big data analytics. Compared to Hadoop MapReduce, Spark is more flexible and orders of magnitude faster. This diagram illustrates the implementation of the algorithm in Spark. The point cloud and the DTM are represented as resilient distributed datasets, or RDDs. RDD is a data handling mechanism in Spark that allows the dataset to be divided into immutable partitions for distributed processing. Each data partition in an RDD is handled by a unique processing core, and the processing of a partition is independent of the global state of the computation as well as the state of other processings. And that is how Spark managed to minimize the demanding synchronization and communication in parallel data processing. The rasterization in our algorithm is formulated as a map function in Spark. That mapping is performed for each individual point, so there is no communication across cores needed at this step. And here you can see we have a slight modification from the algorithm that we mentioned earlier. For a full-scale analysis, we often have multiple DTMs, and each of which may have a different raster coordinate system. So in such a case, a re-rasterization is needed to transform all of the data into an agreed coordinate system for the join. So the re-rasterization is not much different from the point cloud rasterization described earlier. The output of the mapping is a point cloud and a DTM, both indexed by a raster keys in an agreed coordinate system. The analysis continues with the join, which is the most expensive operation in the entire workflow. It is expensive because the data need to be shuffled around the computing cluster to co-locate the point and the DTM records that share the same raster index. Luckily, we don't have to implement the tran operation by ourselves. Spark have some built-in functions to tran data, and it exposed a very easy to use API for us to implement the tran. After the tran, the points are grouped with their corresponding ground elevations, and we only need another map function to extract points that are below the ground level to achieve the ultimate results. The main benefit of using distributed computing here is that we can connect more computing cores to our cluster when we want to shorten the data processing time or when we have more data to process. That approach is usually referred to as scale out, which is an alternative to scale up, which means getting a higher performance machine to achieve the same goal. And here's a small endorsement of the scale out approach. I will leave you some time to read the code by yourself. I hope that the information provided so far are sufficient to justify the first two characteristics of the algorithm, simplicity and scalability. As per the last characteristic, robustness, we have tested the algorithm for all three study areas in UrbanArc: Dublin, Belfast, and Brooklyn in New York. For Belfast and Brooklyn, we were able to obtain the DTMs from open data provided by local governments. We can confirm that the resolution and accuracy of those DTMs are sufficient for our algorithm to succeed. For Dublin, at the moment we have to create a DTM by ourselves. We also tested the algorithm using different kinds of LiDAR point clouds collected by airborne surveys, as well as inexpensive handheld scanners. Despite the different characteristics of the input data, we see that our algorithm works. So I would like to end my presentation here and look for your feedback on the content that I share up to this point.